Principal superposition means that the net displacement of a wave is the sum of individual displacements of waves meeting at a point. Is that clear?
Yes.
So when two waves meet, it is called interference. Okay, so we're gonna talk about interference in a bit. For example, if there is a wave which seems like this, and there's another wave and these two waves are 0-degree phase difference. So when they interfere with each other, they create a wave that's much bigger, which means that if the amplitude of this wave was A and the amplitude of this wave was also A, so now the new wave that is the result of superposition will be of 2A. This sort of interference is called constructive interference. All right, Ikra.
Yes.
So
Can
constructive.
you move a little up?
Yes.
I'm writing.
Okay. Yes. Sure.
Yeah, done.
Okay, Janikra. Now,
Yes.
constructive interference is possible when two or more waves meet at a point with 0-degree phase difference. 0-degree, or you could say with that are in phase. So we can write a broader term. In phase means that it should be 0-degree or 360 degrees and so on, right? Like we talked about phase. Okay, Kram. Now,
Yes.
speaking of this then, the other kind of interference that might occur when, let's suppose, a wave is like this and there's another wave which is like this. Now, wait a second, I didn't make it nice correctly. Okay. So, let me make it like this. Okay, grow like this. Now, when these two combine, you should understand that the amplitude of this wave is, let's suppose, A, and the amplitude of this wave is negative A. The reason is that amplitude is a vector quantity, right?
Yes.
Now, so when they combine, So what you expect is that these two are going to cancel out each other, and what you see is, because a minus a will be 0, so there will be no amplitude. This kind of interference is called destructive interference. In destructive interference, we can say when two or more waves meet at a point that are anti-phase. When we say anti-phase, it means it's 0, it's 180 degree and multiples, 540 and so on, right? Is that clear?
Yes.
Yeah. So naturally it depends on, if it is like what kind of wave it is. Like if it has a different amplitude, obviously some wave will be left. But the thing is, if they both have the same amplitude, then you just need to add the amplitude at every point. That's it. Whatever result you get, that's basically that's explained by principle of superposition, right?
Yes.
Okay. Now, so one of the prime result of a superposition is basically when it creates a stationary wave. Now, stationary waves is created when basically two waves superpose. You can also write meet, that are of these basically three properties. One, they must have same frequency, they have same amplitude, and they must be traveling at same speed in opposite direction. Alright.
Yes.
For example, suppose there is an end that is completely fixed. There is a wire or a rope, with that matter of fact. When you pull the rope up, basically the wave is going to be like this. Now when you push it down, it will create a hump. And when you basically it goes like this, it gets reflected from the fixed end, so it goes like this. And when the new one is generated by you, so as they meet together, they basically create sort of a wave which is called stationary, which doesn't really transfer energy, but it's like it vibrates up and down like this. Is that clear? Or depending on if it's longitudinal or not.
Yes.
Now, one of the ways that we can create stationary waves is using stretch spring and an oscillator. So what you do is that you fact, I'll do it in down. You want to have a table. Now on that table, you have placed an oscillator, and the oscillator basically attaches a string that goes over a frictionless pulley, and then the string on the other end there is a mass hanger that causes the mass to be put, right? So slotted, mass and hanger. Alright, Ikra. Now,
Yeah.
so the frequency of a stationary wave is frequency of the oscillator is adjusted until a stationary wave forms, which means something like that. Okay, now so before we go deeper into this, like that, you should understand that these points that you see right here, these are called, oh my god, nodes. Then the center ones which vibrate the most, these are called antinodes. Then you have nodes, then you have antinode. Usually we write it as N and N. So after each antinode there is an antinode like this. Do you understand, Ikra?
Yes.
Now if you look at the wave, you might realize that this part between one node to another, the distance is like just half lambda, right? Same goes if you look at antinode to antinode. So antinode to antinode is also half lambda. Got it?
Yes.
But between an antinode and a node, only this much wave is there. So it means between node and antinode, it is a quarter lambda. So you got to remember these things. Do you understand, Ikra?
Yes.
Good. Now, so node can be defined as a point with zero displacement and speed. Okay, an antinode, or you could say zero displacement and energy, no energy there. Antinode, a point with maximum displacement and energy. Do you understand?
Yes.
Okay, very nice. Do you get my point now?
Sorry?
Do you understand this?
Yeah,
Okay.
I got.
Now, when stationary waves are created, they can be created in three different ways. Okay. First way is when we create them in a closed, both ends closed system. Okay. So like the one that we're dealing with right now. So in a both closed system, both ends are fixed, which means the string is right now laid down. This one end is a pulley, one end is a oscillator. Do you understand? Yeah. Or it could be the other thing.
Yes.
Now, if I say this is the length of the string, and I give it like, I just cause it to move by just one movement, like once. So what you're gonna witness is that this string is gonna go up because I pulled it up, and now it is going to go down when the stationary wave forms, and it is going to keep on doing this until the energy is dissipated. Understood?
Yes.
This movement, that this frequency that we give is called the first harmonic, which means this is also the fundamental frequency, which means this is the minimum frequency you can give in order to create a stationary wave in this system. Okay?
Yes.
Now if you see this point is a node, this is an antinode, and this is a node. So it means that from a node to another node, we've just learned that it is equal to half lambda. Got it?
Yes.
That basically means that we can say that half lambda is equal to the length of the string right now, and lambda will be equal to 2L divided by 1. Can I write it like this, please? It doesn't matter, right?
Yeah.
Now, since velocity is frequency times lambda, so frequency is v upon lambda. So the frequency can be written as speed over 2L. Okay. I'll just multiply 1 with this, which was here. Intentionally I'm doing this for a reason. I'll let you know in a bit. Okay, is that clear to you?
Yes.
Okay. Now, so we create the second scenario. Now, it is all this. So if I want to create the next frequency wave, obviously I have to increase the frequency. So the next wave will be created like this. So if you plug it 2 times, right, in a certain frequency, it is going to create something like that. Now if you notice, this is a node, this is a node, and this is a node, right?
Yeah.
This much distance is half lambda, and this is half lambda as well. So that means this is called the second harmonic. And 1 lambda is equal to the length of the string. Understood?
Yeah.
Can I write it as 2L over 2? Would you mind?
No.
It would be the same thing, right?
No.
And in terms of frequency, I would like to write it as frequency is equal to V times 2 over 2L. Because lambda was 2L upon 2. So if you put lambda in this equation, it will become that. Please have a look at it. Let me know if you have a question.
Yeah, got it.
Okay. Now on to this third harmonic. So if you go on to the third harmonic, basically, hello, how are you? I hope you're doing well. Can you please tell me which year group and subject you need so I can help you better now? So, the third harmonic would be when you pluck, or the three times, you pluck it and a frequency like this creates a wave. Understood?
Yes.
Now, if you look at it, this is the length, this is the node, 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 node. So it is half lambda from here to here. This is another half lambda from here to here. And this is another half lambda from here to here. Right?
Yeah.
So now this makes it 3 by 2 lambda, which I can write as 2L over 3. Do you understand?
Yes.
And for the frequency I can write F equals to V times 3 over 2L. Now, Ikra, you can draw this please, and then I'll tell you what is happening here. Okay, now if you look at all of these, you might see a pattern. Like first harmonic, there was a 1 here, right? In the second one, there was a 2 here. In the third one, there was a 3 here. So can I say that the general formula for two ends closed would be something like lambda is equal to 2L by n, where n is like 1, 2, 3, 4, which is the number of harmonics. Do you understand this?
Yeah.
And for frequency, it is going to be V times n over 2L, because the same thing, 1, first, second, third. So I can say where n is like 1, 2, 3. So this way you can easily find, let's suppose if they say, okay, give us the frequency of 100 harmonics. So you can just put 100. You should know the speed of the wave and you should know the length of the string. You will definitely be able to find it, right? Do you get my point?
Yes.
Okay. Now the question is that we do understand that what is the speed of a wave, like we do understand how we'll find frequency in lambda, but how would we know the speed of a wave? And speed of a wave can be found out by a very simple formula. So we're writing wave speed on a stretched string, okay, the one that we've shown through a diagram, right, like this one. Okay, so to find that, the formula is V is equal to under root T over mu. Now what are these? V obviously is the speed of wave, T is the tension in string. Generally we find out this by mg. And how do I do that? Whatever the mass we are attaching, right? So it will have a weight mg, which is equal to the tension in the string. Understood? And
Yeah.
then mu is the mass per unit length of the string. So basically you divide the mass of the string divided by its length, so you'll get it right away. Alright, I hope you understand this now.
Yeah, okay.
Okay. The rest things are like the ones that we do in basically the practical. When we'll start unit 3, we'll learn this. Okay. But right now we will talk about
Okay.
other things. Yeah. Cool. Now there are many ways that we can use to find speed of a certain wave, not just the string. And for that we have different, say, ideas. For example, if we're looking at something like we want to find the speed of microwaves in air, so it's very simple. Basically, we want to use a microwave signal generator, right? Like that. And on the other end, we have to keep a metal reflector. Okay.
Yes.
Now, when the microwaves are generated, and a stationary wave is formed like this. So what we use is we use a probe which is connected to a CRO, or it could be any detector for that sense. This is a microwave probe detector. Like it would detect what is the strength of microwave at this point. Okay.
Yes.
Now so at this point, because you know this is a node, there will be a no reading here. Do you understand? So if you move this probe
Yes.
to this side, so when it gets here, it will show you a maximum reading, right? Because this point will be the antinode. And when you move it back here, it will show you 0 again. Do you understand? So when it shows you a 0 reading again, you can find the distance that you have moved from the first 0 to another 0, right? So what we're doing is we are moving the detector in a line to pick up the nodes and antinodes, right? So
Yes.
then what we're doing is we measure the distance between two successive nodes. Obviously, when you do that, then you know between a node to a node, the distance is half lambda. And that is the distance d that you found out. So from here, you can find the distance by multiplying 2 with it, right? Lambda by multiplying 2 with it. And simply,
Yes.
you can use v is equal to f lambda to find the speed, where f is the frequency of signal generator, like that. You got my point?
Yes.
Now, the next thing we can do, that we can use the same phenomena to find the speed of sound, but in a different way. This experiment is called the Kunz dust experiment. So in this experiment, what you're gonna do is you just need a tube and a loudspeaker with known frequency. What happens is that Kunz dust experiment has boric powder in this. You know what boric powder is?
No.
Have you played carom board, like that board game?
Yeah.
Do you see the white powder that we put on it so that things can easily
Yeah.
slide, right? That is very light powder. This is the same. So what happens is when the wave is generated inside this, so a stationary wave is formed like that. Now the antinodes displaces that powder, but nodes have no energy, so the powder begins to build heaps underneath where the nodes are. Do you understand? They
Yeah.
get displaced. So we can easily identify. Okay, this is, let me write it here because I'm gonna use it. Heaps of powder. So we can easily identify where the nodes are. Now, obviously here one node will be here, then the other one will be here, the other and here. So we can find the distance between these nodes. Do you understand?
Yeah.
So find distance between two successive heaps. And that distance is going to give you half lambda because it is node to node distance. You get it? So then you can use V is equal to F lambda, where to find the speed of sound, where F is equal to the frequency of loudspeaker. Understood?
Yeah.
Okay. Now, just one question for you, and then we'll continue this next time. Okay, Ikra, can you please do this?
C.
C. Yeah, that's correct. Very good. All right. That means do you